Hi, welcome to the third lecture on probability from actuarialpath.com. In this lesson, we assign probabilities to the events and compound events that we studied in the second lesson. So that's what we mean by basics of probability theory. In fact, we're going to outline some rules of assigning probabilities to the events that we studied in lesson number 2. So in lesson number 2, we studied sample spaces, events, and compound events. If we have a sample space S, and we have an event A, which is a subset of the sample space, then we could assign a value between 0 and 1 for this event A that we call the probability of A, which we denote by P of A, and that is between 0 and 1. P is a set function from the power set of the power set of S, which is the sample space, into the interval 0 to 1. The power set of A, by the way, is the set which contains all the subsets of S. So you list all the subsets of S if you can, and then put them as members of a big set, then you have a power set. As a matter of fact, what this means is every subset of S could be assigned a value between 0 and 1 that we call the probability of that event. And we assign that probability by using some rules or axioms of probability. These axioms are actually called the Kolmogorov axioms. So Kolmogorov axioms. And the first axiom is that for any event A, which is the subset of a sample space, the probability of A is greater than or equal to 0. That is, for any event A, which is a subset of sample space. And by the way, I should mention that the sample space must be non-empty for a sample space S, which is not empty. Then the set function P satisfies the following. Number 1, the probability of A is greater than or equal to 0 for any event A in the sample space. Number 2, the probability of the sample space is equal to 1. This should not be a surprise. The sample space is the list of all possible outcomes of your experiment. Number 3, if we have events A1, A2, A3, and so on, which are pairwise disjoint, I'm going to explain what I mean by pairwise disjoint. Then the probability of the union of those pairwise disjoint sets, I equals 1 to infinity of AI, is equal to the sum, I equals 1 to infinity of probability of AI. Let me explain this further. First of all, what do I mean by pairwise disjoint? Pairwise disjoint means if I take any two of these events, A1, A2, A3, and so on, let's say I take AI and AJ, and find the intersection between the two, then I get an empty set for I different from J. using Venn diagrams. Maybe this is A1 here, A2, maybe A3 here, and so on, A4, A5, which do not overlap, so they do not have intersection. In other words, they are partitions of the sample space. Since they do not overlap, their intersection is empty set. So this statement means the probability of A1 union A2 union A3 union A4 union A5 and so on is equal to the sum, which is probability of A1 plus probability of A2 plus probability of A3 plus and so on. These axioms give us a foundation on which we can assign probabilities to events in the sample space. As a result or as a consequence of the axioms, we have the following identities. And the first identity or property is that for any A, which is a subset of the sample space, the probability of A complement is equal to 1 minus the probability of A. If you look at that carefully, let's say that's the sample space. We have event A, and anything outside of A is going to be A complement. Note that A and A complement are disjoint, or they are pairwise disjoint. And axiom number 3 tells us if you have events which are pairwise disjoint, then the probability of the union is the sum of the probabilities. Therefore, I must have the probability of A union A complement must be equal to the probability of A plus the probability of A complement. This is by axiom number 3 and by the fact that A and A complement are disjoint. This implies that the probability of what is A union A complement? A union A complement is the sample space. The probability of the sample space is equal to P of A plus P of A complement. By axiom number 2, we know that the probability of the sample space is equal to 1. Therefore, 1 is equal to P of A plus P of A complement. Rewrite that to find probability of A complement is equal to 1 minus the probability of A, which is that. Number 2, probability of empty set or the null set is equal to 0. Note that the sample space intersection empty set is the empty set. Therefore, if two events have no intersection, they should be disjoint. That's the definition of disjoint sets. Therefore, I have S and empty sets to be disjoint sets. If I have disjoint sets, by axiom number 3, I know that the probability of the union of these two sets, S union empty set in this case, should be equal to the sum of the probabilities, P of S plus probability of empty set. The union of S and empty set is S itself. That is equal to P of S plus P of empty set. Rewrite that to find the probability of empty set is equal to the probability of the sample space minus the probability of the sample space, which is 0. Property number 3. For two events A and B, which are subsets of the sample space, we have probability of B minus A is equal to probability of B minus probability of A intersection B. That's the third property. Sorry. Let's show that. B minus A is the following. So let's say I have a sample space. Say that is event A. Let me use a different color. It's event B. B minus A is the region shaded right here. Whatever is in B but not in A. Okay? But what is this? This area or that region is the intersection. So that is the intersection of A and B. And the one in blue is B minus A, which is equal to, by the way, B intersection A complement. We should show that. What you note from here is A intersection B and B intersection A complement, which is B minus A. Those two are disjoint, meaning their intersection is empty set. So you see they don't really overlap. And by axiom number 3 again, if you have two events which are disjoint, then the probability of their union, in this case probability of A intersection B union B intersection A complement, is equal to the sum of the probabilities. Probability of A intersection B plus probability of B intersection A complement. What is the union of those two? The union of those two, that blue union, the one in black, gives you the entire region covered by B. And that is equal to probability of B is equal to probability of A intersection B plus probability of B intersection A complement. Rewrite that to find the probability of B intersection A complement is the probability of B minus probability of A intersection B. And this is B minus A. B intersection A complement is equal to B minus A. Therefore, we have shown that. What if A and B are disjoint? In other words, what if we have something like this? That is A and that is B. In that case, the probability of B minus A, which is going to be equal to the probability of B minus the probability of A intersection B, would simply be equal to the probability of B, because their intersection is empty set, and the probability of an empty set is 0. Property number 4. It is called the inclusion-exclusion principle. For two sets A and B, which are subsets of the sample space, we have the probability of A union B to be equal to the probability of A plus probability of B minus probability of A intersection B. Let's show that. I have a sample space which contains A and B. Let's say that is A, and let me use a different color, and I have B. And this region that I'm going to shade in black is the region covered by the set A. And the region I'm going to shade in blue is the region covered by B minus A. Okay, as you can see, B minus A and the set A are disjoint, or they are mutually exclusive. And by axiom number 3 again, if two sets are mutually exclusive or disjoint, then the probability of their union is the sum of the probabilities. Therefore, the probability of A union B minus A is equal to the probability of A plus probability of B minus A. That is axiom number 3. But what is A union B minus A? A, entire region in black, union, the blue shaded region, is equal to A union B. So the probability of A union B is equal to P of A plus P of B minus A. But we have derived probability of B minus A in the previous property number 3, that said probability of B minus A is equal to probability of B minus probability of A intersection B. So I can substitute P of B minus A by probability of B minus probability of A intersection B. And that gives me the inclusion-exclusion principle. That's what I need to prove right here. So I have shown that. And this is called the inclusion-exclusion principle. In fact, if you have 3 events, A1, A2, and A3, which are subsets of the sample space, then the union, the probability of the union, P of A1 union A2 union A3, is equal to probability of A1 plus probability of A2 plus probability of A3 minus probability of A1 intersection A2 minus probability of A2 intersection A3 minus probability of A1 intersection A3, and finally plus probability of A1 intersection A2 intersection A3.